Welcome to this new session on algebraic structures. In the previous session, we have seen how to verify that given an algebraic structure whether it is a group or not. In the sessions prior to that, we had already talked about what is a group and what are the various properties of groups. Today in this session, we are going to talk about two more properties of group. One is the order of the group and one of the order of an element of the group. So let's begin. A group defined by G comma star where G is a non-empty set and star is a binary operation is called a finite group if the number of the elements in group are finite. See, this is the non-empty set. So this non-empty set can be finite or infinite. So depending upon whether this non-empty set is finite or infinite, the group is deemed to be finite or infinite. So if this is a finite set, then the group that it defines is called a finite group. And if it is an infinite set, then the group that it defines is said to be an infinite group. The finite group example is 0, 1, 2, 3, 4, 5. These are examples of finite set. So the group that is defined by this will be the finite group, and Z the set of integers, R the set of real numbers, Q the set of rational numbers. So these are all infinite sets. So whenever we are defining a group on these sets, it will be deemed to be infinite group. Now, the order of a group is the number of elements in the group. Obviously, the order of a group can only be defined for the finite group. The number of elements in the group, or in other words, the cardinality of the underlying set, is called the order of the group. It is denoted by order of G, O of G, or by using this symbol. A group of order 1 has only the identity element. You cannot have a group of order 0. Why? Because whenever I am talking about group, I have been stressing upon the fact that the set that is making up the group should be a non-empty set. So if there is a single element in the group, that element will be the identity element. So this is what is order of the group. Say for example, we talked about this 1 omega omega square with multiplication. We talked about this group. Then the order of the group is equal to 3. There are 3 elements, 1, 2, 3. Similarly, if I talk about, let us say 1 minus 1 I minus I and multiplication, then the order of this group is equal to 4, as the cardinality of this set is 4. So the order of the group is 4. Now, going one step further, if there is an element A belonging to G, then the smallest positive integer, let me repeat, smallest positive integer n for the element A such that A to the power n is equal to E, where E is the identity element, is called the order of the element A and is denoted by O of A. Let's take a simple example to understand this. Once again, let us take the set 1 omega omega square, where omega is the cube root of unity and the operation multiplication. I know that the identity element for this was 1. So I know that 1 to the power 1 is equal to 1. So the order of the element 1 will be equal to 1. Once again, I know that omega to the power 3 is equal to 1. So the order of the element omega is equal to 3. See, any number less than 3 is not going to give me 1. Omega to the power 1 is omega. Omega to the power 2 is omega square. But omega to the power 3 is omega cube, that is equal to 1, as omega is cube root of unity. So 3 is the smallest positive integer in this case, where omega to the power 3 is equal to 1. Similarly, omega square to the power 3 is equal to 1. See, omega square to the power 3 is same as omega to the power 6, which is omega cube to the power 2, that is 1 square, that is 1. So order of omega square is also 3. Similarly, if I take this set 1 minus 1 I minus I with multiplication, order of 1 is equal to 1. 1 is the identity element. E is the 1. So order of identity element is always 1. Order of identity element is always 1. Order of identity element is always 1. So let's proceed. Now if I take the element -1, I know that -1 square is equal to 1. So order of -1 will be equal to 2. Similarly, I know that I square is equal to -1. So I square that is equal to I to the power 4 will be equal to 1. So the order of I is equal to 4. Similarly, if I take minus I square, it will be minus I square will be -1. So again, minus I square whole square is equal to 1. So order of minus I is also 4. Another important point. I know 1 to the power 1 is equal to 1. 1 is the identity element over here. 1 to the power 2 is also 1. 1 to the power 3 is also 1. 1 to the power 4 is also 1. So what should be the order of 1? This is where this comes into picture, the smallest positive integer. So if a to the power n is equal to e, if a to the power n is equal to e, then order of a is less than equal to n. I know that 1 to the power, let us say 5 is equal to 1. So order of 1 is not equal to 5. It is less than equal to 5. Right? Let's see certain examples. Let us find the order of each element 1, 2, 4, 7, 8, 11, 13, 14, multiplication modulo 15. So identity element, as it is a multiplication operation, usually multiplication operation has the identity element as 1. So 1 being the identity element, the order of 1 will be 1. I have already told you the order of identity element is also always 1. Now multiplication modulo 15 means the result will be divided by 15 and the remainder will be taken. Order of 2. What power? What power should I raise 2 so that the result when divided by 15 will give me 1? I'll repeat. How do I find the order of an element? Here, let us say 2. What is the power to which 2 should be raised so that the result when divided by 15 gives me 1? So in case of 2, it is simply 4. 2 to the power 4 is 16. 16 divided by 15 gives me a remainder of 1. Similarly, order of 4 will be 2. 4 square is 16. So 16 divided by 15 is 1. So order of 4 is 2. Order of 7 is 4. Order of 8 is 4 and so on. So these are the orders of the elements. See something? What is the order of the group over here? 1, 2, 3, 4, 5, 6, 7, 8. Order of the group is 8 and order of elements are 1, 4, 2, 4, 4, 2, 4, 2. See, the order of the element is always coming less than the order of the group. Later on, I am going to prove that this is the case, but it's a thumb rule. The order of the element will always be less than or equal to the order of the group. Let's take another example. Now see this example very carefully. This is an example where many people make mistakes. Order of each element of this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Addition modulo 10. Now the first thing to note is that the operation here is addition. So addition here is operation. So the identity element is 0. Now when I say order, I mean to the power to which an element should be raised. 3 to the power 2, contrary to what our instinct says, 3 to the power 2 does not mean 3 multiplied by 3, but it means 3 plus 3. Why? Because the addition operation is there, not the multiplication operation. So this is something that you have to keep in mind. So 0 is the identity element, so the identity element has the order 1. Now what is the order of 1? How many times should I add 1 so that the resultant when divided by 10 gives me a remainder of 0? So it is 10. If I add 1 10 times, I get 10. 10 gives me 0 when divided by 10. So order of 1 is 10. Order of 2 is 5. Order of 3 is 10. Order of 4 is 5. Order of 5 is 2. For 6 it is 5. For 7 it is 10. For 8 it is 5. For 9 it is 10. Now let us see some properties of the order of an element of a group. The first property, as we have already talked about earlier, is that the order of every element of a finite group is finite and is less than or equal to the order of the group. Let's see how. We have to show that for every element A belonging to G, order of A is less than equal to order of the group. Now let G be a finite group of order n and let A belongs to G. Now G is a group of order n. So that means there will be n elements. But let us try to identify certain elements. Let us say a to the power 0 is equal to the identity element. We have to define an identity element, this being a group. Now I'll have a to the power 1, a to the power 2, a to the power 3 up to a to the power n. And apart from these elements, I have identified a to the power 0 as E. Now, as these are all powers of A, so they will all belong to the group G. We have already talked about group being closed operation. So this binary operation that we define in the group is a closed operation. So a to the power 2, that means a star A will also belong to G. A cube will also belong to G, and so on and so forth. So a to the power 0, which is the identity element, a to the power 1, a to the power 2 up to a to the power n, all belong to the group G. But they are not all distinct elements. Why? Because the order of the group is n and these are n plus 1 elements. So they are not distinct elements. There are two elements out of these n plus 1 elements which are same. See, a to the power 0 to a to the power n, these are n plus 1 elements, whereas there should have been n elements. So, two elements out of these are same. I do not know which are the two elements. They could be a to the power 0, a to the power 1, or they could be a to the power 5, a to the power 100, or whatever. Right? So, but these are not distinct. There are two elements which are same. Let us say the two elements which are same are a to the power j and a to the power k, where j is less than k. Now j can be anything from, j can start from 0 and k can go up to n. But the only point is j is less than k. Now operate both sides by a to the power minus j. So I get a to the power j into a to the power minus j is equal to a to the power k into a to the power minus j. So on left hand side I get a to the power j minus j, that is 0, is equal to a to the power k minus j. Right? Now a to the power 0 that I am getting on this side, a to the power 0 that I am getting on this side is equal to e, as I have already defined. So this is equal to e. And let us assume, let us substitute k minus j by r. So I get a to the power r is equal to a to the power 0. See, the a to the power r is equal to a to the power 0 is equal to e. So I've identified up to this point that a to the power r is equal to e. A to the power r is equal to e. What it means is order of the element A is less than equal to r. We have already discussed order of A does not, a to the power is equal to e does not mean that order of A is r. It means order of A is less than equal to r. Now as k was greater than j, so r is a positive integer which is less than equal to n. So R is a positive integer less than equal to n. So I have order of A which is less than equal to R which is less than equal to n. So I can write as order of A is less than equal to n. But what is n? N is the order of the group. So order of A is less than equal to n, which is order of group. So order of A is less than equal to order of group. Let's take another property. If the element A belonging to G is of order n, then A to the power k is equal to E if and only if n is a divisor of k. Now again, please pay attention. I have used if and only if. That means I have to check for necessary and sufficient condition. In other words, I'll have to perform the proof in two steps. In the first step, I will assume a to the power k is equal to e and prove that n is a divisor of k. And in the second step, I will assume n is a divisor of k and then I will prove a to the power k is equal to e. Let's take the first case. Let a to the power k is equal to e and we need to show that n is a divisor of k. Right? As k is an integer, and n is positive. N is positive. Why? Because n is the order. It can only be positive. So by divisibility theorem, we can say that there exist integers p and q such that k is equal to np plus q. That means when I'm dividing k by n, I'm getting p as quotient and q as remainder. So k is equal to np plus q, where q ranges from 0 to greater than equal to 0 and less than n. You divide anything by n, you can get the remainder from 0 up to n minus 1. So a to the power k is equal to a to the power np plus q, or a to the power np into a to the power q. Now what is a to the power np? I can write it as a to the power n to the power p into a to the power q. But okay, we know that the order of the element A is n. That means a to the power n is equal to e. That is already known to us. So a to the power n is already equal to e. So I have e to the power p, a to the power q. Now we also know that e is the idempotent element. That means any power raised to the e does not make any difference. E to the power raised e to the power anything x is still equal to e. So I have e dot a to the power q, that is equal to a to the power q. So I get a to the power k is equal to a to the power q. So a to the power k is equal to a to the power q, and our assumption was a to the power k is equal to e. Now, if I say a to the power q is equal to e, that means order of a is less than equal to q, but q is less than n, and order of a is equal to n. Now we are in a dilemma. If order of a is equal to n, that means n is the smallest positive integer such that a to the power n is equal to e, and I am having q less than n and a to the power q is equal to e. So this is a dilemma and it cannot be true unless we ignore this and we say that q is equal to 0. Smallest positive integer. Now we do not consider this to be the order and we simply say that if q is equal to 0, then all our problems are solved. Q is less than n and a to the power 0 will be the identity element, obviously. So a to the power 0 is the identity element, and q is also less than n, and q can be 0 remainder. You can get a remainder of 0. So this is possible if and only if q is equal to 0. So if q is equal to 0, k is equal to np plus q reduces to k is equal to np. K is equal to np, and if I say k is equal to np where p is an integer, so that means n is a divisor of k. So I have shown the first part of the proof. Now for the second part of the proof, let n is a divisor of k. We will assume this to be true, and then I will try to show this. So if n is a divisor of k, that means there exists a integer p such that k is equal to np. N is a divisor of k, that means we multiply something to n to get k. So let that something be the integer p. K is equal to np. So if k is equal to np, now what do we do? A to the power k is equal to a to the power np, that is a to the power n to the power p. We know that a to the power n is equal to e. So we get e to the power p, which is equal to e. So a to the power k is equal to e. So we have shown the property from both the sides. So these are some of the properties of order of groups. Right? Till the next time, thank you.